Swayam Prabha. Digital India. Educated India.
As well as in the postgraduate programs, right. So, many of you would have a certain understanding of fluid mechanics. The objective of this lecture is to visualize how these equations are derived or do come up based upon the concepts that we have learned earlier from our introduction to the mathematical preliminaries that included our Gauss divergence theorem, and from a vector perspective rather than from an equation perspective. Also, how we can apply our numerical and analytical methods for these. Now, numerical methods in fluid mechanics that comes under the a huge domain of computational fluid dynamics. CFD itself is a very vast topic, something to be covered in a separate lecture series, and there are many other lecture series available through NPTEL or through other modes which cover CFD in depth. Analytical approaches are done in during our UG. We usually study them under steady state, and gradually we move on towards transient. That is something we will cover in today's lecture. So, we will base our lecture on the concepts of fluid mechanics, trying to attain an understanding of how these equations are formed, what are they, how are they related to the former equations that we have derived, either the Navier's equation from solid mechanics or the diffusion equation from heat transfer. How is our fluid mechanics equation are relevant. Okay. So, we start by the continuity equation. So, in any fluid mechanics system, I am not going into an introduction of what a fluid is and as such, since we are doing modeling, we understand that there is a fluid flowing through a structure. There are two main equations or two main conservation laws to follow. The first is a conservation of mass, that is our continuity equation, and second is the conservation of linear momentum. In many cases, if there is a vortex, and we also need to do the conservation of angular momentum. Okay. So, with that we can start with the conservation of mass. So, mass conservation. The typical approach for a mass conservation is to have a volumetric element. Say that this is a volumetric element of dimension. If we take this along x axis, this is a y axis, and this is a z axis. If we use our own terms, then it will be x1, this was the notation we have been using, x1, x2, x3, and we have let us say that this length is dx, the height is dy, and the width is dz. Again you can say it is dx1, dx2, and dx3. Okay. So, whatever notation you are comfortable with. I prefer to use a 1, 2, 3 rather than x, y, z for a reason, and that it matches with our index notation. So, we have covered index notation in depth, and we have been using it over and over when we have done heat and mass transfer or in the solid mechanics segment. Okay. So, say in this volume some mass is entering, say that this is rho u1 on this area, that is dx2, dx3, and some mass is leaving, say this is rho u1 plus del by del x1 of rho u1 along dx2, dx3. Okay. And likewise in the y direction and in the z direction. So, we are considering, and this is the standard differential approach and that we are using. I will again go back to our integral approach once we have covered and got the quarter formulation. So, consider a rectangular prism. Which is our control volume. And from here onwards I will call control volume as CV. of dimension dx1, dx2, dx3. So, the net volume is dx1 cross dx2 cross dx3. So, if we take along the x1 direction, the inlet stream along 1, the inlet flow rate would be the density times u1 times dx2 times dx3, and the exit or outlet will be equals to rho u1 plus del by del x1 of rho u1, and there is a dx1 missing from here, dx1, dx2, dx3. Okay. So, the net mass change slash stored along x1 will be equals to it is your inlet minus your outlet, which will be your rho u1 dx2 dx3 minus of rho u1 plus del by del x is u1 and we find out it is equals to minus del by del x1 rho u1 dx1 dx2 dx3. Okay. Along all three directions, I belongs to 1, 2, 3, the net mass stored in the control volume will be equals to minus del by del x1 of rho u1 minus del by del x2 of rho u2 minus del by del x3 of rho u3 along dx1, dx2 and dx3. Okay. So, for this small control volume, and this is our mass stored. This looks something very familiar. You can see that we can write this in short as del xi of rho ui from our summation notation along del x1, del x2, del x3. If I is repeated, we are adding this over, and this in terms of vector is a gradient. So, this is del dot with rho u vector into this into the volume, that is dV. Okay. Now, the mass stored can also be expressed as the density, the change in density with time into the volume of the body, right. So, that is the mass stored, how much the density is changing. If the volume is fixed and if mass is increasing, then the density will rise, right. And if we equate these two things, so equating the two, from conservation of mass, we can get that that del by del t of dV will be equals to minus del dot rho u dV. We can integrate this over the entire volume V, bring everything to one side, and we have del rho by del t plus the divergence of rho u to dV is equals to 0. Now, let us take a minute to realize this equation. So, the first term, it explains how the density of the body is changing, and that is the transiency in terms of the density, right. So, this is your transient term or the unsteady term. The second term, it explains, it is the divergence of a vector quantity. Now, we have studied earlier that divergence gives the net outflux or influx. So, the divergence of rho u, where rho u is a mass rate or in terms of mass rate per unit volume, it tells us how much mass is leaving the system. or how much mass is entering the system. So, summation of the two gives us that the net density change is equals to the net mass if the volume is fixed, and if mass is increasing then the density will rise, right. And if we equate these two things, so equating the two, from conservation of mass, we can get that that del by del t of dV will be equals to minus del dot rho u dV. We can integrate this over the entire volume V, bring everything to one side, and we have del rho by del t plus the divergence of rho u to dV is equals to 0. Now, let us take a minute term. It explains how the density of the body is changing, and that is the transiency in terms of the density, right. So, this is your transient term or the unsteady term. The second term, it explains, it is the divergence of a vector quantity. Now, we have studied earlier that divergence gives the net outflux or influx. So, the divergence of rho u, where rho u is a mass rate, or in terms of mass rate per unit volume, it tells us how much mass is leaving the system, or how much mass is entering the system. So, summation of the two gives us that the net density change is equals to the net mass influx into the system. The summation of the two is equals to 0, and that is the conservation of mass. So, that insight I would like you to develop when you see the continuity equation, that why is the density changing? Because there is a net influx of mass in, and if the density is reducing, then there is a net outflux of mass going out from the control volume. For now, we have taken the control volume to be a cuboid or a rectangular prism. However, it could be anything else, right? It could be any arbitrary shape. Since V is arbitrary, so we can go over here. Now, since the V is an arbitrary volume, then for any volume V or any smaller segment of this volume V, that is also an arbitrary volume, and this integrand should be the same, and therefore, for it to be 0, this integrand needs to be 0. So, this del rho by del t plus divergence of rho u should be equals to 0, and this is our continuity equation. In terms of Einstein summation notation, this is del by del xi of rho ui. Now, this continuity equation we can derive it from an integral approach as well. If you would revisit the mass transfer class or the mass transfer lecture, you would see that we have derived this based upon the mass flux, and we have seen how the mass flux is based upon the diffusive mass flux and convective mass flux. In this case, there is no diffusion. Right? There is a fluid flowing through a control volume in and out from all directions. So, we can, instead of taking a cuboidal shape, we can take an arbitrary volume V, which is bound by a surface S, which is equals to del V. Right. We have an internal storage in the body. So, this internal storage m dot stored is the same as last time, as del rho by del t into dV over the volume V, and the net mass, say some mass is entering, some mass is leaving. We can say that the mass from the surface, mass flux from the surface, that is leaving or entering, over del V or the surface S is equals to rho into u vector dotted with the surface normal into dA or ds. Okay. By conservation of mass, what we can say is that m dot stored plus m dot surface is equals to 0. Right. This is a net outflux. So, the outflux plus the stored should be equals to 0, and that is your conservation of mass, and this will give you integral over volume V del rho by del t dV plus integral over the surface del V rho u vector dot n cap over the surface ds. This is equals to 0. Now, we can change this surface integral to a volume integral. using the Gauss divergence theorem. And this we have done earlier. Let us first do this part in this slide. So, del V of rho u vector dot n cap ds is equals to integral over volume divergence of rho u vector dv. If we substitute this and take everything into one integral, we will get the same formula as last time. And for any arbitrary volume, again the integrand should be 0. So, del rho by del t plus del dot rho u vector is equals to 0. So, we get the same formulation as an outcome. Okay. Now, if the fluid is like water or a liquid, and most of the liquids are incompressible. So, for an incompressible fluid, our density is a constant and does not change. In that case, the first term becomes 0 and the density comes out from the second term and can be made equals to 0, and we will get del dot u vector is equals to 0, which in terms of the index notation is del u I by del x I, that is equals to del u 1 by del x 1 plus del u 2 by del x 2 plus del u 3 by del x 3 is equals to 0. Right. So, this is our continuity equation for an incompressible fluid. And this is our continuity equation for a compressible fluid. Make sense? Okay. Now, we will go on to the Navier-Stokes equation. So, now what we have done is we have done the conservation of mass, we will go on to the conservation of linear momentum, right. So, Navier-Stokes equation is derived from the Newton's second law, that is a conservation of linear momentum. We can assume a rectangular cuboidal geometry. Right, again this is x 1, this is x 2 and this is x 3. Some momentum is entering and some momentum is leaving the system, and there is some momentum stored. So, we can say that this is force conservation. So, force due to momentum change is equals to del by del t of the mass of this control volume into the velocity vector v, that is our transient term. Now, you can also depend upon x, y and z, that is each momentum along each direction and can be varied, and that will be del by del t along x direction. It will be m plus u vector plus del by del x 1 of mu vector into dx 1 minus this inlet, right. So, this is mu vector and this is mu vector along each direction. So, this will not u vector, this will be along u 1. You can take it vector for now, plus m del by del x 1 of mu vector, let me write it clearly. So, it will be del by del x 1 of mu vector into dx minus mu vector. This is along x direction. What do we get from here? We are getting this term gets cancelled out. Likewise, for the y direction, del by del x 2 mu vector into dx 2 plus del by del x 3 mu vector into dx 3, the brackets closed. Okay. Now, what we can do instead of making this partial, let us make it a complete make a normal derivative, because x, y and x is a function of x itself, y is a function of y and z is a function of z. So, x 1 is a function of x 1 along the x direction, x 2 is along y direction and z 2 is along z direction. So, these derivatives will apply only onto these x 1, x 2, x 3, and we can find out that the momentum conservation is del by del t of mu, since u it was a function of x1, x2, x3 and t, but each x1, x2, x3 are not a function of the other directions. That is why we have converted this partial into a total derivative. We will find it is del by del x1 of mu vector into dx1 by dt, mu vector dx2 by dt plus del by del x3 of mu vector into dx3 by dt. So, we can see that our momentum equation can be rewritten in terms of our index notation or our vectorial notation as f momentum equals to del by del t of mu vector plus, and you can see that these 1s and 1s correspond and 2 and 2 correspond and 3 and 3 correspond. That means it is a dot product between u vector dotted with this gradient term along with the m of u. Okay. So, you have a u dot del that is a dot product of our velocity vector with our gradient vector into m of u. Okay. Now, this is slightly different from our mass conservation, and when you are deriving it, I do not expect that you will memorize, but you should realize what is happening. In the case of mass conservations, we are taking each component of velocity, multiply it with the density along x, along y, along z, and then we were adding them up together. In this case, we are not doing that. We are taking the entire velocity vector along each direction, multiplying it with the mass, right. So, it is in terms, it is rho u u, right. So, rho into u vector, and it is giving you and then you are taking a divergence, right, of that quantity along that direction. So, rather than considering it as a summation of the individual masses, it is not a summation. Each direction of the velocity can have and can be dependent on the other direction. So, u1 can depend upon x1, x2, x3 and time t, right. So, that is why we need to consider every direction of velocity. By this approach, you are taking this as an entire vector, and when you will do it in a numerical program, then you will make a vector as in the form of a matrix of n cross 1, that is 3 cross 1 or 2 cross 1, and you will solve this accordingly. So, you will have u1, u2, u3 as a vector in a matrix when you do a numerical programming. Okay. So, this is done in terms of the index notation. Let me just remove this dash because it looks like a tensor. Okay. So, f momentum of I therefore is equals to del by del t of mu I plus uj del by del xj of mu I. Okay. So, this is our first term. Then we have other forces. So, we can have our force due to gravity. The force due to gravity f vector g will be equals to integral of rho g vector into dv. Okay. We have not had the integral part of this, since we are doing it over this control volume with a volume of dv. So, we need to integrate everything with respect to dv. Since mass is there, let us write in terms of dv. So, f momentum along I is equals to integral over volume v, mass is rho dv. So, I just want to make sure that you are following this along, that although I have written mass in terms of density, it can be translated into density, right. That is easy enough to do. Okay. In terms of index notation, this will be rho gi to dv. Okay. Then we have the force due to pressure. And I will later on tell you where this pressure force comes, or what is the implication of this pressure force. As of now, let's take it as such, as the integral of minus the gradient of the pressure force, the pressure, that is P del I del j into dv. Okay, that is equals to integral of minus del P by del xi to dv. You can see that I is the non-repeating index in all of these. Then let us come to the most interesting part, and that is the force due to viscosity. Okay. So, the viscous force is integral over volume of the divergence of the shear stress tensor into dV, which is equals to the, or this is the deviatory component of the shear stress tensor, that is integral over volume V del tau I j by del x j into dV. Now, what is this tau I j? This tau I j term is equals to mu times the del u I by del x j plus del u j by del x I. That is your, so again if you are, since you are coming from solid mechanics, please let me repeat this, u is not the displacement, u is the velocity in this case. The two look the same, right. U is used as velocity in the case of fluid mechanics and is used as displacement in the case of solid mechanics. So, please do not confuse between the two, since fluid it depends upon the shear rate. So, this is our shear rate, and the shear stress is the viscosity times the shear rate. We have one more term, and that is our 2 by 3, then that comes from the volumetric component of mu into u del u k by del x k to del I j. Okay. So, del tau I j by del x j therefore, will be equals to mu times del square u I by del x j del x j. I am not writing del x j square because index needs to be repeated and shown, plus del square u j by del x j del x I minus 2 by 3 of mu of del square u k by del x j del x k to del I j. Okay. Now, if it is del I j, then you can replace I with j, and this will become del square u k by del x I del x k. You can then combine this term with this term. You can see that j is repeating, in this case k is repeating, I is the open index. So, this becomes mu times del square u I by del x j del x j, this is the only different term, plus 1 by 3 mu times del square u k by del x k del x I, okay, where again k is added over and I is a repeating index. All right. So far is good, we are working it out. So, we can then substitute this into our force. So, our force due to viscosity comes out to be integral over volume mu times del square u I, if you can also write k as j del x j plus 1 by 3 del square u j by del x j del x I. I am exchanging k and j so that you get into a habit that repeating index can be replaced, can be exchanged. If k are repeating, you can write any variable, that does not have a problem, that is not a problem, right. So, you can use del u k by del x k, del u j by del x j, that is the same thing. Okay. So, please start getting into a habit for these things. Now, you have all the forces. So, by the conservation of linear momentum, we can have that F due to momentum is equals to F due to gravity plus F due to pressure plus F due to viscosity. Let us put everything together. So, we will have an integration of del by del t of rho u I plus u j del rho u I by del x j of dV is equals to integral of rho g I minus, we are taking all the volume integrals in one bracket, del p over del x I plus mu del square u I by del x j plus mu by 3 del square u k del x k del x I dV, and let us write it as j so that we are consistent. Okay. So, this is our entire expression, right, and we can again take for an arbitrary volume. we are doing the same treatment. We bring everything to the left into one volumetric integral, and that integrand is 0, and then we rearrange or reshuffle the terms, and we will get del by del t of rho ui plus uj del by del xj of rho ui plus rho gi minus del p by del xi plus mu times del squared ui by del xj del xj plus mu by 3 times del square uj by del xj del xi. This is our continuity equation, in which this is our Navier-Stokes equation considering compressibility or compressible flow. Okay. So, this is our compressibility effect, right, and this rho in the integral is our compressibility effect. For an incompressible flow, our rho is a constant. So, we can divide the entire equation by rho. Another thing that comes up is that del uk by del xk or del uj by del xj is equals to 0 from continuity equation. So, this last term becomes 0, right. It is del uj by del xj and del by del xi of that. So, this term becomes 0, and what we will get is del by del t of ui plus uj del by del xj of rho ui to rho gi is equals to rho term is gone. So, ui, this rho term is gone. So, gi minus 1 by rho del p by del xi plus mu over rho is nu, that is a kinematic viscosity, del square ui by del xj del xj, and this is the ns for incompressible flow. So, this ns for incompressible flow. Okay. In terms of a vector notation, this is del by del t of u vector plus u vector dot and the gradient vector of u vector is equals to g vector minus 1 by rho gradient of pressure p plus kinematic viscosity, the Laplacian of the u vector. Okay. So, by now you are familiar. So, we can see that all the forces we have considered from different directions, and those forces we have considered body force, we have considered pressure force, we have considered viscous forces, we have taken into consideration the effects of compressibility and what terms will be ignored in the case the flow is incompressible. So, with that now let us see where this pressure term comes. So, the actual or the shorter form of the equation that is called the Cauchy momentum equation. So, the Cauchy momentum equation is a simplified version of it. This says that rho du vector by dt is equals to the divergence of the stress tensor plus the force vector, right. This has our transient and our convective terms. Okay. For those who are unaware or those who have not seen the Navier-Stokes equation before, the first term is our transient term, the second term is due to convection, that is due to the motion of the fluid through the bulk. Third is our body force, fourth is our pressure, and the fifth is our viscous effects. Okay. So, it has a so this is our material derivative, that is del u by del t plus u dot del of u. Now, our stress tensor in this case that is sigma ij, our stress tensor is minus p del ij plus some tau ij. This is our hydrostatic component, and I have taken it as negative because it is compressive on the body. Hydrostatic pressure is compressive on the body, and this is our deviatory component, We have talked about hydrostatic and deviatoric in detail when we did the solid mechanics lectures. So, if you go back a few lectures, you will find the concepts for these. The deviatoric will only cause shape change without volumetric changes, and the hydrostatic will cause volumetric change without shape change, right. So, the del sigma ij by del xj therefore is equals to minus del p by del xj of del ij plus del tau ij by del xj, right. And this is where the pressure term comes. Since del ij you can exchange I and j, that is a property. So, del sigma ij by del xj therefore equals to del p by del xi plus del tau ij by del xj. That gives us, integrate this over the volume, you will find that this is your pressure force and this is your viscous force. So, that is the origin of your pressure term, and then the deviatoric component is, or the deviatoric stress tensor is what gives you the viscous terms. Okay. If that is clear, then we will start taking up a few analytical solutions. Couette flow and Poisson flow are quite common when we do UG level mechanics or fluid mechanics. So, let us just see how we can represent these equations. So, we are taking two flat walls, the bottom wall is fixed and the top wall is moved with some velocity u, right. This is separated by a distance h. So, what we want to, and this is our x1 direction, this is our x2 direction. Okay. So, we are considering a plane wall where the top wall moves with a velocity u. Okay. Again, from our continuity equation, we will have this is 2 dimensional, just write it 2 dimensional. Now, flow is along the x1 direction. So, u2 is equals to 0. If u2 equals to 0, which implies that del u1 by del x1 equals to 0, or u1 is not a function of x1 and therefore, is only a function of x2. So, u1 is only a function of x2. We are also considering steady state. Therefore, there is no time dependence. Now, let us take a look at the NS equation along the u1 component. So, that will be del u1 by del t plus u1 del u1 by del x1 plus u2 del u1 by del x2, ignore the third direction for now, is equals to minus g1 plus 1 by rho del p by del x1 plus nu del square u1 by del x1 square plus del square u1 by del x2 square. Okay. Now, we can take out some terms. It is transient, it is steady state. So, this term goes away. u2 is 0. So, this term goes away. u1 is a function of only u2, du1 by dx1 is 0. So, this term goes away. There is no gravity effect along the one direction. So, this term goes away. There is no pressure gradient. So, this term goes away. Okay. u1 is not a function of x1, again this term goes away. So, only thing that is left is nu del square u1, and you can, instead of writing del, we can take the full derivative d square u1 by dx2 square equals to 0, so this is the second order derivative. We need two boundary conditions. So, our boundary conditions are that u1 at x2 equals to 0 is 0, that is the bottom wall is fixed and is a no slip condition, and u1 at x2 is equals to h is equals to capital U. If we take this and if we integrate twice, then u1 of x2 is equals to c1 x2 plus c2. If we put these boundary conditions in here, we will find that u1, let me rewrite this, u1 of x2 will be equals to capital U of x2 over capital H. This is the solution for a Couette flow, where the flow at a given point is a straight line, where the top wall is at the velocity of u and the bottom wall is at 0. If we look at the Hagen-Poiseuille flow, then the Hagen-Poiseuille flow is through a pipe, it is a cylindrical pipe, Now we are changing coordinate systems, and this is our z coordinate and this is our radial coordinate r. So we are consider a cylindrical pipe under steady state. If it is cylindrical, then you can also consider that there is a radial symmetry. Again, from the continuity equation, we find that del u r by del r plus 1 by r del u theta by del theta plus del u z by del z equals to 0. We can see that the flow is along z direction. So, u r equals to u theta equals to 0. From here, del u r by del r equals to 0, which implies that u r is only a function of z. Again, we are considering steady state. Now, let us look at the NS equation along the z direction. So, if you take the z direction for the NS equation, then you have del u z by del t plus u r del u z by del r plus u theta over r del u z by del theta plus u z del u z by del z equals to minus g z plus 1 by rho del p by del z plus nu. So, it is 1 by r del by del r of r del u z by del r plus 1 by r square del square u z by del theta square del square u z by del z square. Okay. So, this is our entire NS equation. Let us remove a few terms from here. So, this is 0, this is a steady state. Again, u r is not dependent on u z is not dependent on r, u r and u theta is 0. These terms go away, this term goes away. There is no gravity effect. Now, there is a linear pressure gradient, there is a linear pressure change along z direction, which means that the dp by dz is a constant. So, we will have this term. Again, from these, this term goes away, this term goes away, and we are only left with that. So, our equation stands as this is plus and this is minus. Okay. Let us go back one slide and let us see if missed the signs again earlier. This is minus, this is plus. Okay. Now, we are good. So, we have if you take rho and multiply, that is mu over r d by dr of r du z by dr is equals to dp by dz. We need two boundary conditions. First, this is again u z. So, u z at r equals to 0 should be finite or bounded, and u z at r equals to r should be equals to 0. So, at the wall it should be 0. Okay. Now, if you solve for this, you will find out that u z of r will come out to be equals to 1 by 4 mu dp by dz of r square plus a natural log of r plus p. Now, at r equals to 0, to be finite, a needs to be equals to 0, otherwise log term will become infinite, negative infinity. And if you put the other term, then the b term, it comes out to be equals to 1 by 4. This is a minus sign over here. So, it comes out to 1 by 4 mu dp by dz of r square. So, again a is equals to 0, b is equals to 1 by 4 mu. Let us go back. This should be plus, this should be minus. Hence, our velocity profile u z of r will be equals to 1 by 4 mu dp by dz of small r square minus capital R square. So, we have some velocity profile, and that velocity profile is along the z direction, and it is due to this pressure gradient dp by dz. dp by dz is negative, that means that your inlet pressure should be more than the outlet pressure. So, if this is negative, then uz is positive and vice versa, right. So, that should be the case. If your inlet is at a smaller pressure than outlet, then the flow is going in the backward direction, and if the inlet is at a higher pressure than the outlet, then the flow is going in the forward direction. So, this dp by dz determines the flow. This will be maximum at r equals to 0, and this will be minimum or actually equals to 0 at r equals to r at the wall condition. So, this is our Hagen-Pursley. Right. So, now you have an understanding of how these equations behave. Let us try to normalize these equations and see what we can get. So, if we normalize our equation, let us normalize, we have done this before for mass transfer for solid mechanics, in which we try to get some constants out, right. So, our velocity the u vector can be done by some capital U, say some free stream velocity. Our x can be, so if x is a vector along the length direction, any L direction. The time we can normalize with some capital T. Say our pressure is normalized with some P naught minus P v, some pressure difference. Okay. From our continuity equation, was del ui by del xi was equals to 0, which implies that capital U over capital L of del cap dot u cap is equals to 0, or del u cap I by del xi cap is equals to 0, it is del cap dot u cap. So, straightforward, right. Now, from NS equation, this is where it becomes interesting. Our NS equation is rho u vector by del t plus u vector dot the del by del x vector, the gradient vector of u vector, equals to g minus 1 by rho gradient of p plus nu Laplacian square of the u vector. Okay. Now, if we normalize this becomes u over t del u cap by del t cap plus u square over L u cap dot del cap u cap equals to g minus, this becomes p naught minus p v over rho into L del cap p cap plus nu u over L square del cap square u cap. Now, let us divide by the convective term, that is u square over L throughout. So, if we divide this, the equation that we will likewise get will be L over u t del u cap by del t cap plus this term is gone, u cap dot del cap of u cap equals to some g L over u square minus this p naught minus p v over rho u square del cap of p cap plus nu over u L of del cap square into u cap. Okay. This becomes our normalized equation. Now, we have several terms which we can consider. All of these terms are some dimensionless terms. So, what are these dimensional terms? The first one is L over u t. This is called the Strouhal number or S, and that gives us a ratio of the Eulerian inertia, and that is the transient term to the convective inertia. The second one is this P naught minus P v over half rho u square. So, you can multiply this by half and half on the top. This is called our cavitation number. So, if there is a pressure difference or sigma, and this if it is greater than 1, then there is no cavitation. If we just have one pressure normalization and say if we just take P naught over half rho u square instead of P naught minus P v, then this is called the Euler number EU, and which is the ratio of your pressure force to the inertial force. And then this term is very well known. So, UL over nu, I do not think I need any introductions for this, is the Reynolds number, RE, and that is your inertial force to viscous force. And finally, this G term, this body force term, if you take a square root of the inverse of this, u square over GL, that is called the Froude number, Fr, and that is a ratio of the square root of the inertial force divided by the gravitational force. Okay. Now, why did we express everything non-dimensionally, and what is the purpose of all of these numbers? It is it's a matter of simplification. For example, if a flow has a very high viscosity and the Reynolds number is very small, so Reynolds number less than 1, in that case we can ignore the convective terms because our viscous terms becomes very dominant. If we have a system in which the Froude number is very small, that is the gravitational effects are dominant, which we have to consider the gravity. If the Froude number is very large, that is inertial forces dominate over our gravitational forces, then we can ignore our gravitational term or the body force term. Right. So, an understanding of these numbers helps us simplify this massive Navier-Stokes equation into something which is simpler, something that we can easily apply into our analysis. So, where do we need convection, where do we not need convection, we can determine using these numbers. All right. Now, let us take a brief example of how to approach an unsteady flow problem. So, let us take a cylinder. So, this is a cylinder. Again, this is our z direction, this is our r direction. Initially, the cylinder is so an infinite cylinder which is filled with fluid, is initially at rest. It suddenly starts to move. With a u velocity. Right. So, this and this will start to move with a u velocity all of a sudden. And initially, where the velocity was 0, initially at rest, it will start trying to get the flow will try to catch up with this, and gradually you will come to the free stream velocity, that is u. Right. So, this is your transiency. Now, this is a transient problem, which means that from the continuity equation, so you understand the problem, right? You have a cylinder filled with fluid which is at rest, and you start pulling the cylinder. So, the fluid, the walls will immediately move, right. So, the fluid attached to the walls will move with the u velocity, but the central fluid is still to see that effect, and gradually the profile will build up to the free stream velocity, that is the u velocity. If that is the case, then del u r by del r plus 1 by r del u theta by del theta plus del u z by del z equals to 0. Again, this r term and theta term are gone, and u z is only a function of r and time t. It is radially symmetric. Okay. Then we go to the NS equation along this z direction. Now, what do we get? So, along the z direction, you will have this rho del u z by del t. This term is required. Then u r del u z by del r plus u theta over r del u z by del theta plus u z del u z by del z is equals to, this is rho g z minus del p by del z plus mu. This will be del square u z by del r square plus 1 by r del u z by del r plus 1 by r square del square u z by del theta square plus del square u z by del z square. Okay. Now, we can make some modifications. U r and u theta are 0. There is only flow in the z direction. Okay. U z is a function of r. So, this term goes away. Likewise, these two terms goes away. There is no gravity, this term goes away. There is no pressure effect, this term goes away. Now, we can write the simplified equation. So, no gravity along z, so g z is 0 and del p along z is equals to 0, or rather we can say that p is not a function of z. So, our equation simplifies down to rho del u z by del t equals to mu over r del by del r of r del u z by del r. Now, this equation is a parabolic equation. So, unlike our Navier's equation, which was a wave equation in solid mechanics, although we have used the conservation of linear momentum, but the equation that we get from the Navier-Stokes is a diffusion equation or a parabolic equation. So, this will behave very similar to your heat transfer problem. Okay. So, we need our initial condition will be that u z at r and time 0 will be equals to 0, that is at rest, and our boundary conditions will be that u z at 0 comma t should be finite or bounded, and u z at r comma t will be equals to capital U. Now, if we normalize this equation or non-dimensionalize this equation, we can take u cap as u minus u z over u. Why we took this is to modify the boundary condition slightly to make it easier. R cap as r over r, and t cap you can take t over t and later on find what capital T is, but I am just writing it down for you. You can try it out on your own what this capital T and why it is r square over nu. Now these terms, when you substitute into your equation, what you will get is that u cap over del t cap equals to del square u cap over del r cap square plus 1 by r cap del u cap by del r cap becomes your equation. And again u cap at r cap comma 0, your initial condition becomes 1, and your two boundary conditions u cap at 0 comma t hat is finite, that remains the same, and u hat at 1 comma t becomes equals to 0. These becomes your boundary conditions. If you want to solve this, this is a Sturm-Liouville problem. And we solve it by the separation of variables. So, I would like you to try it first before you look into the solutions that I am doing. We will break it down into r as a function of r cap and t as a function of t cap, right. And if you put it in, our equation becomes dt by dt, I am skipping one step, is equals to 1 by r d square r by dr hat square plus 1 by r hat dr by dr hat equals to minus lambda square. If you solve this for the time, and I am going over it quickly because you have already done this before when you have done heat transfer, and r is equals to b of j naught. This is a Bessel function outcome, right, unlike a sine function, it is a Bessel function, plus c of y 0 into lambda r hat. Now, if we put our boundary conditions into this, then c is equals to 0 at r cap equals to 0, because y 0 of 0 is unbounded. At r equals to 1, we can find lambda n such that j 0 of lambda n becomes equals to 0. Okay, so, we can find the solution for this. Therefore, u hat of r cap comma t cap becomes summation n equals to 1 to infinity a n exponential of minus lambda n square t hat plus j 0 of lambda n r hat. To find a n, we can use the orthogonality principle of J0, and from the orthogonality principle we have that u hat of r hat comma 0 is 1, so summation n equals to 1 to infinity a n J0 lambda n into r hat. If you solve for this, a n comes out to be equals to 2 over lambda n into J1 of lambda n. Therefore, your u hat of r hat comma t hat will be equals to 2 times summation n equals to 1 to infinity 1 by lambda n J1 lambda n exponential of minus lambda n square t J naught lambda n into r hat. So, this becomes our solution. Again, we can see that there is an exponential decay and then the J naught term exists. So, this is our Bessel function. You could solve this analytically as well as numerically using computational fluid dynamics techniques, something that you can explore from the other NPTEL or the other lecture notes. So, with this lecture we will finish up fluid mechanics and we have a sense of understanding of what these terms are and how a fluid mechanics equation can be handled analytically. So, in the next lecture we will take up our electromagnetism and then consequently electrochemistry. So, thank you for listening.